This is Math 2020 Lecture 35, and we'll be covering section 11.5 today. It's a short lecture. It's about alternating series. So what is an alternating series? An alternating series is a series of the following form. Summation minus 1 to the n, b sub n, maybe n goes from 0 to infinity or something like that, or maybe n equals 1 to infinity. But in any case, this will be where b sub n is always greater than 0, always positive. So this will be of the form b sub 0 minus b sub 1 plus b sub 2 minus b sub 3, etc. Or you can start off with n equals 1 to infinity and have the series alternate in this way. B sub 1 minus negative b sub 1 plus b sub 2 minus b sub 3, etc. So these are alternating. Here's an example to keep in mind. Summation n goes from 0, n goes from 1 to infinity, minus 1 to the n minus 1 over n. So n is starting at 1, so you're going to get 1 minus a half plus a third minus a fourth plus a fifth minus a sixth, etc. Okay, so that's an alternating series, and I want to develop a test for testing alternating series, whether they converge or not. So the alternating series test says the following. If I want this in black, if the alternating series minus 1 to the n, b sub n, is alternating, and if the following is true, if the positive terms associated with the series are decreasing or non-increasing for all n, and also the limit as n goes to infinity of b sub n is 0, then the series converges. So it's important to note here that one does not need strictly decreasing. It could be less than or equal to, but you also need this condition that the limit of the nth term goes to 0. Okay, so I'm going to give a proof of this, a sketch of proof of this result to explain why it's true. Proof. Okay, so here's the idea. So let's start looking at the various terms of the series, but I'm going to only look at the partial sums which are of even index. So S2 is B1 minus B2. S4 is B1 minus B2 plus B3 minus B4. Now B1 minus B2 is positive, right? And B3 minus B4 is also positive. So therefore, if we add to S4, S2, B3 minus B4 to S4, we get something that's bigger than or equal to S2. And when I didn't mean positive, I mean non-negative. Okay, and similarly, if we keep going, the even partial sums of the series have the following structure. You take the previous even partial sum and add b2n minus 1 minus B2n to it, and that's going to be greater than or equal to S2n minus 2. What this shows, this shows the following sequence of inequalities. S2 is bigger than or equal to 0, is less than or equal to S3, S4 is less than or equal to S5, S6, sorry, I have to only look at the even partial sums. And that's the first fact. So this is increasing. Now, furthermore, the sequence S2n can be also rewritten as B1 minus B2 minus B3 minus B4 minus B5. We can rewrite it like this. And it goes up to, what does it go up to? Dot, 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 minus, dot, 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 minus B2n minus 1 minus B2n. Now, every term in parentheses is positive and is being subtracted off of B1. So B1 is an upper bounds, upper bounds, S2n. So now we have a sequence which is monotone. So it's monotone and is bounded. So that implies the limit as Sn as n goes to infinity of S2n exists. Well, that's what it means essentially for the series to converge, even though I'm looking at only the even partial sums. But we can just look at the even partial sums. That's enough for the limit to exist. Okay, so that's the idea of the proof. The proof is done. Okay. So for the rest of today, what I'm going to do is I'm just going to do some examples. I'm going to do 5 examples of this and just applying this test. And that's all I'm going to do, and that's it for the week. Okay, so example 1 would be summation minus 1 to the n minus 1 over n goes from 1 to infinity. So this is the series 1 minus a half plus a third minus a fourth, etc. So b sub n is 1 over n, and note that 1 over n is greater than or equal to 1 over n plus 1. In fact, it's strictly less than. So the terms are decreasing. B sub n plus 1 is less than or equal to b sub n. That checks. The other thing we need to check is that the limit of b sub n as n goes to infinity is 0, and that's obviously true for 1 over n. So the series converges. So we got that. Here's example 2. So let's try the following example. The sum minus 1 to the n over 2n plus 1. Okay, so n goes from 1 to infinity. Oops. Okay, so b sub n here is n over 2n plus 1. And so the first condition is we need to know whether n over 2n plus 1 is decreasing or non-increasing. So is that true? Well, I suggest we can study this by looking at the function f of x equals x over 2x plus 1. And then we can, well, what we can do is, there are 2 ways to solve this. You can do it using calculus. So you can do calculus, look at f prime of x, which is given by the quotient rule, which is going to be 2x plus 1 times 1, derivative of x is 1, minus x over the derivative of 2x plus 1, which is 2 over 2x plus 1 squared, and then you're going to get 1 over 2x plus 1 squared, it looks like to me, and f prime of x is, and this is going to be greater than 0. So for all x, so we have a problem here. This is saying the function is increasing. So and you can even see it's increasing. So for example, if when n equals 1, the first term of the sort of sequence bn, you get 1 over 3, and then you get 2 over 2 times 2 is 4, plus 1 is 5, which well, actually, that's less than a third. Then you have 3 over 2 times 3, which is 6 3/7, which is more than a third. It seems to be increasing. Okay, so this is not going to work. And so we have to study this differently. We cannot use the test. The criteria for the test don't work. What does that tell us? The test is inadequate for studying the problem. However, we can consider the following thing. We know we can consider the limit as n goes to infinity of -1 to the n over 2n plus 1. Now, if we look at n over 2n plus 1 and ignore the signs, n over 2n plus 1 tends to 1/2, right? So let's look on the number line 1/2. Here's 1/2. As n, now let's look at the signed version of this, -1 to the n over 2n plus 1. As n gets larger, the points oscillate between, on both sides of 1/2. Sorry, this is, let me, a lot of noise in the background. So, so on both sides of 1/2, the points are zeroing in, and they get closer and closer to 1/2. So the limit is not equal to 0. And therefore, this is not the alternating series test. By the test for divergence, or the so-called divergence test, since the limit of a sub n, this is a sub n, is not 0, the series diverges. So the alternating series test could not apply here, does not apply. Okay, let's go to another problem. Example 3. So the sum -1 to the n squared over n cubed plus 1. Let's say n equals 0 to infinity. Okay, so b sub n, let's try to apply the alternating series test. So b sub n is n squared over n cubed plus 1. We need to know whether it's non-increasing. So let's look at the function f of x equals x squared over x cubed plus 1. We can do calculus. F prime of x equals x cubed plus 1 times 2x minus x squared times 3x squared over x cubed plus 1 squared, which is equal to, okay, so the numerator simplifies to 2x to the 4th plus 2x minus 3x to the 4th over x cubed plus 1 squared. And that's going to give me what? That's going to give me x. I'm going to factor out an x times 2 minus x to the 4th over x cubed plus 1 squared. Okay, the reason I'm writing it this way is that if x is at least 2, for example, the numerator is negative. So this is less than 0 if x is, say, greater than 2, greater than or equal to 2. That's enough. So therefore, it's decreasing. So it's decreasing. And that tells us that n squared over n cubed plus 1 is decreasing. Now that's the first method of dealing with this. The second way to do it, here's another way to do it. N squared over n cubed plus 1 is decreasing if and only if its reciprocal is increasing. So n cubed plus 1 over n squared is the reciprocal. And we just have to check that that's true. But what is n cubed plus 1 over n squared? That's n, by breaking up the fraction, that's n plus 1 over n squared. Now, it's pretty clear that since n is varying over integers, that this is increasing. Since this is a fraction less than 1, and this is an integer, so this is clearly increasing. So therefore, n squared over n cubed plus 1 is decreasing. So we've checked the first condition of the alternating series test. B sub n is decreasing, or is at least non-increasing. The second thing we need to know is the limit as n goes to infinity of n squared over n cubed plus 1. We have to compute it. And by not dividing numerator and denominator by, this is a standard limit calculation, n cubed, you get 1 over n on the top and n 1 plus 1 over n cubed on the bottom, and this limit is 0. So this also checks out. So therefore, the series converges by the alternating series test. You always, when you justify these things, these are like proofs you're giving, you have to give the reasons. And I'm giving you the reason why it converges. I verified the conditions of the alternating series test, and I applied them. And then the last line of the proofs, you would say it either diverges because, or it converges because. So now we come to example 4, which is summation minus 1 to the n minus 1, and goes from 1 to infinity of n e to the minus n. Okay, so b sub n we can write as n over e to the n. And we need to know it's non-increasing, and we need to know the limit is 0. So let's first of all show it's non-increasing using calculus. So f of x is x over e to the x. So f prime of x is given by e to the x times 1 minus x times e to the x over e to the x quantity squared, which is e to the 2x. So that's 1 minus x. We can factor out an e to the x, and then this becomes 1 minus x over e to the x. Now, if x, the denominator is positive, so if x is greater than 1, its f prime of x is negative, so it's decreasing. So therefore, b sub n is decreasing. So that's the first thing we have to check. The second thing we need to check is the limit. So the limit as n goes to infinity of n over e to the n. Well, that's the same as the limit as x goes to infinity of x over e to the x. And now if you plug in, if you let x plug in infinity, you get an indeterminate form of type infinity over infinity, so we can use L'Hopital. That tells us that this limit that we're trying to compute is the limit as x goes to infinity of the derivative of x, which is 1, over the derivative of e to the x, which is e to the x. So now as x goes to infinity, this becomes 0. The denominator blows up, so therefore the reciprocal, which is 1 over e to the x, goes to 0. So therefore, the limit as n goes to infinity of b sub n is equal to 0, so that checks. So therefore, the series converges by the alternating series test. Good. So for my last example, I want to consider the following example, which is from the text. Summation n goes from 1 to infinity minus 1 to the n minus 1 over e to the n. This is an alternating series. Oops, this is the wrong way. I didn't write the correct series down. It's over n to the p, so we fix a number p. So this is asking us for which p is this convergent? So when is it convergent? So that's the question. Okay, so let me just write down the first few terms. It's 1 minus 1 over 2 to the p plus 1 over 3 to the p minus etc. Okay, so b sub n is 1 over n to the p. And the question is when is this decreasing? Well, you can just by inspection, b sub n is less than n plus 1 is less than or equal to b sub n if p is positive, because in the exponent of n is positive and these numbers are decreasing. And that's if and only if. So I should write if and only if here. So that's true. That case checks out. So then we're left with the second condition. What's the limit as n goes to infinity of b sub n? That's the limit as n goes to infinity of 1 over n to the p. Now, if p is positive, this is obviously 0. So this checks out. So therefore, if p is greater than 0, then the series converges by the alternating series test. Okay, so what happens if p is not greater than 0? So if p is less than or equal to 0, what's happening? So then I claim we can use the divergence test to show that it diverges. Because 1 over n to the p minus 1 to the n over n to the p is equal to minus 1 to the n to the minus p in this case. So now if this exponent is now greater than or equal to 0, and if it's equal to 0, then you get n to the minus p is 1, and you're getting minus 1 to the n. That's oscillating back and forth. It doesn't converge to 0. And if p is strictly less than 0, then n to the minus p is a positive exponent in p, and that's going to blow up. So the limit minus 1 to the n over n to the p is not going to exist. So therefore, it diverges by the divergence test. So yeah, so that's the story here, and I think that's it for today. We now computed 5 examples, which I said, and we're done with this very, very short section. So have a good weekend. Okay.